There we go. All right. Good morning for realsies this time. Right. So again, we're starting lecture set 5 today. Lecture set 1, we did fundamentals, talked about some definitions, for example, that of a variable and types of designs. Lecture set 2, we talked about graphics for data. We split that into 2 categories. So we had visualization for qualitative data, visualization for quantitative data. And then we talked about summary statistics like the mean, the median, the mode, standard deviation, percentiles, etc. Lecture set 3 was the probability unit. This made up the first 3 questions on assignment number 2. This tends to be the trickiest unit in the course for students. I think conceptually understanding how to visualize the sample space and how to draw events out of a sample space tends to create issues. The counting rule adds another layer of complexity to that particular suite of problems. So I usually what I find is that particular assignment both serves as a bit of it serves as a bit of a shock to the system. It can be a little overwhelming, but we start to streamline more, especially with the lecture set 5 material. So you're going to start to see a lot of continuation in particular topic or particular skills as we progress to the next 4 lecture sets. Yeah, about 4 lecture sets. In lecture set number 4, we talked about probability distributions in the case that the variable is discrete. So we talked about the general case, which is where we had the probability table. So this would be questions 4 and question 5 on assignment 2. And then we discussed how to compute the expected value, how to compute the mean, how to draw probabilities out of that table. Following that, we talked about the binomial distribution, which is a specific type of discrete probability distribution. What we're going to talk about in lecture set number 5 are continuous probability distributions. So the idea is similar in that we are still focused on evaluating the probability of observing a certain event, but the type of variable that we are working with is changing compared to lecture set 4. After we do a general introduction to the continuous probability distributions, we will talk about a specific continuous probability distribution, which is called the normal distribution. And the normal distribution is a distribution that we are going to see in this lecture set 6, lecture set 7, and lecture set 8. So there's a continuous flow of what we can do and how we're going to work with this distribution for about the next, month of the course roughly. So as I mentioned before, we really start to kind of streamline and the topics start to become more closely synced compared to how they were in the beginning. All right, so as I mentioned, we're going to talk about 2 major topics in this lecture set. The definition of a continuous probability distribution, which is a fairly short portion of the lecture set, and then the normal distribution, which is a very specific type of continuous probability distribution, and it is a very common type of continuous probability distribution. It's a distribution that you see very often throughout, or a distribution that we would prefer to work with across many fields. And we're going to see examples of how you would work with this across many fields in a couple of weeks when we start talking about intervals and hypothesis testing. Okay, so first thing first, again, in lecture set 4, we talked about the discrete probability distribution. Again, a discrete random variable is a variable that effectively admits whole number values. So for example, x being equal to 2, 3, 4, strictly, that would be an example of a discrete random variable. It takes on a whole number value and there's a fixed number of values. The continuous random variable is different from the discrete random variable in that it's not described in the same type of set notation that I wrote in red on slide 3. The continuous random variables can take on any value between fixed points. So they can be measured very precisely up to any number of decimal places that we might be interested in. They don't even necessarily have to be bounded. So a continuous random variable, like the one that we would find in a normal distribution, has no upper limit and no lower limit. They exist across the entire real line and stretch from negative infinity to positive infinity. Okay, so just in terms of how we conceptualize that variable, it's very different from the discrete case. All right. When we talked about the distribution of the data set back in lecture set 2, we talked about two major ways of describing the shape of the data. That was through symmetry and skewness, or symmetry versus skewness, or modality. In general, we sort of said, like, if you have a histogram of the data, you can kind of draw like a smooth curve over top of the histogram to represent the shape. We can think of that curve as being a density curve. Okay, so continuous random variables emit curves, whereas discrete random variables emitted those probability histograms. Right, so you might remember, for example, we had on one of the one of the earlier slides in lecture set 4, we had something that looks like this. So 2, 3, 4. Here we would have the probability that x is equal to x, and then we were just drawing our bars to the probability of observing that value. The probability histogram is unique to the discrete random variable. With the continuous random variable, we emit density curves. So there's another difference between the two. On slide 4, I have an example of a density curve for some continuous random variable that we can call capital X. So you can see that this density curve is a smooth curve that sits on top, or that sits on top of the range of X. So in this illustration, we have a density curve that doesn't have any particular bound. So even though it kind of looks like the curve is meeting the axis at, like, this would be like roughly approximately 42, and this would be approximately 3, for example, it's actually never directly touching the axis. So the lines extend infinitely in either direction. Now, there are two major properties of a density curve. One, it always has to sit on or above the horizontal axis. So this here is the horizontal axis, and the curve is sitting on top of it. So the curve has to run across the value of X. The other property of the density curve is that the area beneath it has to be equal to 1. So in the second plot here, the part shaded in red, this represents the area under the curve, okay? And the total size of that area is 1. That's the most it can ever be. And the entire area under the density curve has to be equal to 1. Okay. Okay, so the way that we work with density curves, given that the total area under the curve is equal to 1, we interpret the area under the curve as being the probability of observing a certain event. Now, unlike discrete random variables, when you have a continuous random variable, there is no concept of being equal to. So when we talk about events for continuous random variables, we're always talking about ranges. So for example, X, the continuous random variable, has to be less than some number. It has to be greater than some number. It can be between two numbers, or it can be outside of two numbers. But it always has to be described using a range, because again, there's no concept of being equal to in the continuous case. So for example, in the first plot shown here, what I have shaded is the area that is below 30. So this would be a representation of x being less than 30. So the area under the curve that's less than 30 represents the probability that x is less than 30. In the second plot, we have a similar idea, except here we're bounded between 20 and 30. So this would be the probability that x is between 20 and 30. Okay, in the general case, in order for us to find these probabilities, we would have to integrate the curve between the limits that we are interested in. This is not a technique that we are going to talk about in this class. So for our purposes, finding area underneath the curve is going to be done using tables of values or additional information about the area that exists underneath the curve. So for example, let's suppose that we wanted to find the probability that x sits between -5 and -4. The first thing that we can do in this case, or really the only thing that we can do in this case, is identify that particular probability by shading underneath the curve, because we don't have any additional information about what exists or what the area between certain values is equal to in this particular illustration. So we want to find the area that represents the probability that x is between -5 and -4. Okay, so this area is simply represented by the region under the curve that sits between -5 and -4. Okay. So this shaded part here represents the probability that -5 is less than x is less than -4. As we progress through the lecture set, we will learn how to evaluate this probability. So we will learn how to calculate it. In this particular first example, we don't have any information yet. So all we can do is visualize the area. Visualizing the area under the curve is a very important and a very useful skill. If we know the shape of the curve, it's always beneficial to us to sketch out what it is that we are looking for. And as you can see here, building that sketch is quite straightforward. All right, so let's return to a similar problem. We have the same density curve from 1A. Now we are being told that the area below -4 is equal to 0.159, and the area below 6 is equal to 0.933. And then we are asked, what is the probability that x is between -4 and 6? Okay, let's start by sketching out what we know. So we are told the area below -4 is equal to 0.159. So here's -4, and we are being told that this area here is a size of square, is a size of 0.159. Okay, so that's basically just saying that the probability that x is less than -4 is equal to 0.159. Okay. Okay, the second thing that we are told is that the area below +6 is 0.933. Okay, so this is going to be a similar sketch. We start here at +6 now. We're being told that this entire area, everything that's below 6 is 0.933. So we can write in a bigger letter here, 0.933. Okay. And that's going to be this whole thing all the way down. Right? And just like before, this is just telling us the probability that x is less than 6 is 0.933. Okay. Now, what we want to know is the probability that x is between -4 and -6. This is what we're interested in. Okay, so the area between -4 and 6, we've already learned how to sketch that. So I know this is getting a little bit overwhelming with color and highlighter, but this would be in blue here, the area that we are looking for. Okay. So we have the entire area underneath 6. We have the area underneath -4. We want to get the area between those two values. So to do that, all we have to do is subtract off the part that's below -4 from the part that's below 6. So we can show that the probability -4 is less than x is less than 6 is equal to the probability that x is less than 6 minus the probability that x is less than -4, which is 0.933 minus 0.159, which is and now I'm going to embarrass myself. 13 minus 9 is 4. 12 minus 5 is 7. 8774. Yeah, cool. I can still subtract. Okay, so this is a very common exercise when looking for probability under a continuous curve. So this recognition that the area between two values is found by subtracting the area below the upper limit, or rather is found by subtracting the area below the lower limit from the area below the upper limit, is something that we will see very often throughout this particular unit and even in some of the subsequent units that we're going to study after lecture set 5. But that's the general idea of how we can find area under a continuous curve if we don't know anything about the properties of the curve outside of a couple of different select areas underneath said curve. Right. Any questions so far? All right, so now we're going to turn our focus to the normal distribution. As I had mentioned at the start of class, the normal distribution is a distribution that we will see very often from now until actually the conclusion of the course. In particular, over the next 4 lecture sets, we will talk about the normal distribution quite often. Okay, the normal distribution is a specific or very common continuous probability distribution. It actually has 2 names, normal, which is I think what it's most commonly referred to, or Gaussian, which is what it's typically referred to in the statistical literature. The name Gaussian comes from Carl Gauss, who discovered or defined the distribution. Okay, so named after that researcher. The normal distribution is a symmetric bell curve. So we've actually already seen 2 examples of a symmetric bell curve. We just worked with one in the previous illustration, and the illustration before that, when we first shaded the area under the curve, is also a bell curve. The normal distribution, or the symmetric bell curves that are normally distributed, are also called normal curves. So the definition of a normal curve is just symmetric bell curve. What does it mean for a bell curve to be symmetric? Well, it just means that at the middle of the curve, we have the mean of the distribution, and then the way that the curve spans out from the mean is defined by the standard deviation. Okay. For example, on slide 9, I have 4 different normal curves, okay? The first normal curve has a parameter set mu equals 0, sigma equal 1, all right? So that means that this curve has a mean of 0. So you can see that the curve is centered at the mean. So mu always describes the middle or where the peak of the normal curve is located. The standard deviation describes how the curve falls out from the mean. To understand the effect of the standard deviation, you really have to use comparison between different curves. So for example, in the second illustration, I have another normal curve that's centered at 0. Sorry, I don't know why I wrote 2 here. That would be very confusing. So I have another normal curve that's centered at 0. But you can see here that sigma is now equal to 3. So we have a larger standard deviation. You can see that what happens in this case is that the area gets pushed further away from the mean. So as a result, when sigma goes up, the peak goes down and the tails come out. So sigma increases, leads to peak decreasing. Okay, I'm going to use the arrows. Sigma going up means peak goes down, means tails go up. Okay, so when sigma increases, the peak, so the middle comes down and the tails come out. If you recall the definition of standard deviation, it describes basically the average distance of the data points from the mean. So if the standard deviation is increasing, the curve is reflecting that the data is getting further from the mean, which is why we have this sort of the larger tails and the lower peak. Okay, in the next 2 illustrations, we can see a similar idea. So now we are centered at 2. Okay, and then in the second illustration here, we are again centered at 2. But now you can see that sigma has decreased to a half. So now we can see the opposite effect. When sigma goes down, the peak comes up and the tails, or sorry, the peak comes up and the tails go down. So similarly to the first description, when our standard deviation decreases, all of the data moves closer to the mean. And that's what this final illustration is showing us, is that situation. So sigma has gone to a half, which has caused the data to move closer to the mean and the peak to pull up. Any questions so far? Okay, so the question is, if we are only given one area, do we minus it from 1? It depends on what you're looking for. If in the previous illustration, for example, if you only had one area here and you still wanted the probability between being negative, the probability that x is between -4 and 6, it would be impossible to solve it. So it just depends on what the problem is asking for. If you're not given enough information to solve it, then you can't solve it. But with that being said, what we are building towards is finding area underneath the normal curve. And for finding area under the normal curve, we will always be able to figure out any particular region because we have what is called the normal table. And I'll introduce that in a little bit. Good. Okay. Any other questions? Okay. Okay, on slide 10, I'm just recapping the discussion from slide 9. So this is just summarizing how the mean controls the peak or the center of the curve and how the standard deviation either inflates or deflates the tails. Okay, when we are working with bell-shaped curves, so normal curves, for example, there are some areas that are defined based off of that shape, okay? So we can use what is called the empirical rule to find the area between 1, 2, and 3 standard deviations of the mean. As we progress through the lecture set, we will learn how to find areas regardless of its distance from the mean based off of a standard deviation. But the empirical rule can be sort of a shorthand or quick way of working out certain areas if you know you have a bell curve and you are interested in just certain standard deviations from the mean. Okay, so visually, the empirical rule would look something like this. First, okay, we'll do it in the general case. So I'm giving myself lots of room here. Okay, so this is going to be my horizontal axis. Okay. At the middle of the axis, I'm going to put mu. And then I'm going to mark standard deviations from the mean at approximately equal distances. So this is going to be mu plus sigma, mu plus 2 sigma, mu plus 3 sigma. This is going to be mu minus sigma, mu minus 2 sigma, mu minus 3 sigma. Okay, so I'm moving one standard deviation away from the mean. Now I'm going to try and sketch a bell curve. This is supposed to be symmetric about mu, so it's not going to be a perfect sketch, but I'm going to do my best. Okay, so it's going to look something like this. Right? That's not terrible. So the idea is like this is perfectly symmetric about mu. So on each side of the center, it's a mirror image of the other side. Okay, and then this is the middle right here. Okay, so a few quick facts about bell curves. Again, total area under the curve is equal to 1. Yeah. Okay. Any valid probability density curve has to have an area equal to 1 underneath its density curve. If that isn't true, it's not a valid curve. The normal curves are symmetric about mu. Okay. So that means on each side of mu, I have 50% of the area. Okay, so total area under curve is equal to 1. They are symmetric about mu. So on each side of mu, area under the curve is 0.5. Okay, now the empirical rule, which is what is stated on the slide, has 3 different properties. Between 1 standard deviation of the mean, you have 68% of the information. And this is where trying to sketch it becomes difficult, but I'm going to do my best here. Okay. So this is going to be 0.68. Okay. So this illustration is supposed to show that between the red bars, we have 68% of the area under the curve, or the area under the curve between the 2 red bars is 0.68. Okay, between 2 standard deviations, we have 0.95. So I'll use a different color this time, but it's the same idea. Okay, and here we have 0.95. All right, so between the 2 blue bars, we have 0.95 of the area. All right, and then lastly, I don't know. Between 3 standard deviations, we have 99.7% of the area. Okay, so these 3 properties, which belong to the empirical rule, are true for any symmetric bell curve. So every single normal curve would adhere to these 3 rules. And in general, any symmetric bell curve, even if it's not a normal curve, would also adhere to these rules. So we can always use the empirical rule to find area between certain standard deviations of the mean, or approximations of the area between certain standard deviations of the mean, if we know we are working with a symmetric bell curve. Any questions? All right. So if we know that the population that we are collecting information from is normally distributed, we say that we have a normally distributed population. It's not very, not an overly large leap there. If we know that the values from the population that we are working with are approximately normal, or that is the shape of the population we are studying is approximately normal, we say that we have an approximately normal distribution. In either case, if we want to find the probability associated with certain outcomes, and we know that we are working with a normally distributed population, then we can use the standard normal table. So the purpose of the next several illustrations are to illustrate how we can find area underneath a normal curve. For any normal curve, we can find area using what is called the standard normal table. Okay. All right, first off, I've said twice now standard normal, right? When something is standard normal, it means that it has a mean of 0 and a standard deviation of 1, okay? So the standard normal distribution is a specific type of normal distribution. In general, any symmetric bell curve that, well, any normal curve is defined by a mean and a standard deviation. So mu can be any number on the real line and sigma could be any number on the real line. When mu is 0 and sigma equals 1, we call it the standard normal. So this is a specific normal curve. It is one of the infinite number of normal curves. Okay, the standard normal curve adheres to all of the same properties of any density curve, and it also adheres to the empirical rule. Okay, so the total area underneath the standard normal curve, just like any normal curve, is equal to 1. There are no bounds in either direction. So the normal curve technically stretches from negative infinity to positive infinity. So it never actually touches the x-axis. The standard normal curve is symmetric about its mean, like all normal curves are. But because mu is 0, that means it is symmetric about 0 in this case. So it follows that the empirical rule would be defined for -1 to 1, -2 to 2, and -3 to 3. So for example, 99.7% of the area under the curve is between -3 and 3, because that's 3 standard deviations from the mean on each side of the mean. All right. So our objective is to find area underneath the normal curve, underneath any normal curve. To do that, we are going to work with the standard normal table. The standard normal table is a table that gives values or normal values between -3.99 and +3.99. And essentially what the table does is it just gives us area underneath the curve. When we are working with values from the standard normal table, we typically refer to them as z-scores. The reason for this will become more clear in about 4 or 5 exercises. We typically designate a z-score using a lower z. So effectively, capital X will be a random variable from any normal population or any normal curve. Capital Z is a standard normal random variable. So we associate the letter Z with being standard normal. Okay. And again, the objective here is to learn how to use the table to find area underneath the curve. That's our complete objective for the first 4 or 5 exercises. Okay. So here's our first exercise. We want to find the area to the left of z equals -1.96. Okay, so this is our z-score. Okay, we are told the z-score is -1.96, and we want the area to the left. Left meaning below. Okay, so the area to the left of z equals -1.96 is the same thing as the probability that z is less than -1.96, because area under the curve represents the probability of an event. So being to the left of -1.96 is the same as finding the probability that the z-score is less than -1.96. In the diagram shown below, and I'm just going to zoom in here so you can get a closer look. In the diagram shown below, we have an illustration of the standard normal curve, right? So we can see that this curve is centered at 0 because for any standard normal curve, mu is equal to 0. Okay, now the starting point for this problem is to mark down what we know. So we know that we want the probability that z is less than -1.96. So on the plot here, I have found z equals -1.96. And then below, I have shaded the area that I'm looking for. Again, visualization of what you're trying to find is a very helpful practice or skill. I personally, when working with normal curves, like to shade what I'm looking for because it helps me visualize the problem. Technically, you don't have to do this. There's no requirement to shade or sketch the region, but it is helpful, especially when we start getting into more complex areas like double sides of opposite objects or in between values. In this particular situation, we're in a very basic, this is a very basic type of problem. This would be the easiest normal, or this would be the easiest illustration of finding area under the normal curve, because we are strictly looking for area below a particular z-score. Okay, so we understand what we want. We've sketched what we want. How do I actually find this area? Well, here is page 1 of my standard normal table. So the way that the, oh, sorry, here we go. The way that the normal table works is we are given z-scores on the axis, on the axes here, right? So here and here, these are z-scores, okay? You can see that we have an illustration of what the curve or what the table is actually giving us right here. What this is telling us is that the values inside the table represent areas to the left of a particular z-score. Okay. So the table gives area to the left of a z-score. All right, so we want to know the area to the left of z equals negative 1.96. So to do this, we start by looking at our axis and finding negative 1.96. So here's negative 1.9. You can see that all standard normal tables are giving z-scores to 2 decimal places of accuracy. So in general, we always need to round to 2 decimal places when we are given a z-score. So we have negative 1.906. Now we find the intersection of those 2 values. So negative 1.96 intersects here at 0.250. Okay, so that means that the area to the left of z equals negative 1.96 is of a size 0.025. Right, so that red shaded part there is a size of 0.025, which means that the area to the left of negative 1.96 is equal to 0.0250, and therefore the probability that z is less than negative 1.96 is equal to 0.0250. Okay, so that's our first illustration. If we were given the area to one side and had to find the area of another side without z, would we do 1 minus area of the side given? Yeah, that would work. Yeah. So if you have, for example, the area below negative 1 and you want the area above negative 1, you can just subtract from 1. I'm going to post the tables on the website. They might already be in the lab merged section under statistical tables, but I'll post them in the course content of our lecture section as well. Oh, sorry, any other questions? Yeah, you can do that, Daniela, but I'll send you the complete tables. There's actually 2 pages to it. We've only seen 1 page so far, so. Okay, the second example. In this illustration, we're being asked to find the area to the left of 1.28. So we want to know how much area is below z equals 1.28, which again is the exact same thing as the probability that z is less than 1.28. All right, so it's the same setup. First, we're still working with a z-score, which means that we are working with standard normal distribution. So again, you can see here that on my normal curve, I am centered at 0. Now I have marked down where z equals 1.28, these are z-scores, equals 1.28 is located. Okay, so this is it's a generated image, so it's very precise, but in general, we just use rough sketches so that we know what the area looks like. So here z is 1.28. I want the area to the left, so below 1.28. So that means that I'm looking for the probability that z is less than 1.28. Okay, standard normal value, a z-score, standard normal table shown here. Okay, this is page 2 of the standard normal table. You can see that the setup is the same. So these are all z-scores. But the difference is that we are now working with positive values. So the standard normal table has 2 pages, a page for negative scores and a page for positive scores. When we're working with the negative scores, we have area that is below the curve strictly on the negative side of 0. So those are all areas that are going to be below 0.5. When we're working with the positive side of the table, we have areas below positive z-scores. So these are areas below numbers that are to the right of 0. So they're now all going to be greater than 0.5 by definition. Okay, so to find the area to the left of 1.28, we start by looking for 1.2, and then we come across the 0.08. So you can see that this works in the exact same way as example 1. We're just working with a positive number rather than a negative number. Okay, we find the intersection, which is 0.8997. All right, and this is going to be the area below the table to the left of 1.28. So this whole red shaded thing here, this is a size of 0.8997. Okay, so then because area under the curve is the same thing as a probability, since the area to the left of 1.28 is 0.8997, the probability that a z-score is less than 1.28 is 0.8997. Any questions? Okay, in example 3, we are now going to see a situation where we are looking for area to the right of a particular z-score. So in this illustration, we are being asked to find the area to the right of negative 1.28. So we want to know how much area is above z equals negative 1.28 underneath the standard normal curve. So we want to know the probability that Z exceeds negative 1.28. So the setup for this is going to be the same as before. Here's my normal curve. This curve is again centered at 0. Okay, so we can draw the straight line from 0 here. Okay, and then I'm going to mark down on the curve where negative 1.28 is. So here is Z is equal to negative 1.28. And what I want to find is the area to the right of Z equals negative 1.28. So I want the area above this value. Okay, so we go back to our normal curve or our normal table. We have a negative Z score. So we're going to use page 1 of the table. We're going to look up negative 1.28. So here's negative 1.208, and that gives us 0.1003. Okay, so this area that we just found is the area to the left of negative 1.28. So recall or remember that the standard normal table always gives area to the left. So that means that this unshaded part here, this is a size of 0.1003. We want to know the area to the right of negative 1.28. Since the total area underneath the curve is equal to 1, we can take the area to the left that we just looked up and subtract that from 1 to find area to the right. Okay, so here you can see that calculation. The probability that Z exceeds negative 1.28 is equal to 1 minus 0.1003. This is the value from the table. Okay, and then this is the area above negative 1.28. Okay, so the red shaded part here is a size of 0.8997. Any questions? Okay. So you may have noticed that the solution to example 2 and the solution to example 3 were the same number. This is because of the symmetry underneath the curve. So again, on each side of 0, you have a mirror image of the other side of the curve. So 50% of the area is above 0, 50% of the area is below 0. In the illustration below, I'm trying to highlight this feature. So for example, the area that's below negative 1.28 is the same size as the area that is above positive 1.28. Okay. Therefore, the area above negative the area to the right of Z equals negative 1.28 is the same as the area to the left of Z is positive 1.28. Right of negative 1.28, left of positive 1.28. Now, the point of bringing this up now is not to create confusion. It's simply to highlight that as you get more comfortable working with normal curves, you can start to exploit the symmetry to get to certain answers a little bit faster. For example, in the previous exercise, we subtracted from 1. This is a perfectly valid and acceptable technique, and this is how you should do it in the beginning. But once you become more comfortable with the curve, you could actually say, well, I know that the area to the right of this negative, to the left of the negative is the same as the area to the area to the right of the negative is the same as the area to the left of the positive. So you could just look up the positive, for example. But these are slightly more advanced techniques that just come with comfort and working with the normal curve. All right, example 4, we want to find the area between two values. So we're being asked to find the area between negative 1.96 and positive 1.96. Okay, so we start in the same way that we did before. We're going to sketch the values. So here's my standard normal curve. Again, I am centered at 0. Okay, here it would be Z equals positive 1.96. And here is Z equals negative 1.96. Okay, so I want the area between positive 1.96 and negative 1.96. All right, so to do this, the first thing that I can do is recognize that the probability that that negative 1.96 is less than Z is less than positive 1.96 is equal to the probability that Z is less than 1.96 minus the probability that Z is less than negative 1.96. Okay, so this is the same technique we actually talked about in one of the introductory examples for the lecture set. So these are both areas to the left. I have the area to the left of positive 1.96 and I have the area to the left of negative 1.96. So I go to my standard normal tables. So here's page 1 and page 2 beside each other. This would be how we would use the table in the most general setting. We would put the pages beside each other and we would have our negatives flowing into our positives. I'm going to look up my values. So here's negative 1.96. Here's positive 1.96. Okay, so I'm being told that the area to the left of negative 1.96 is 0.025, and I'm being told that the area to the left of positive 1.96 is 0.975. So many numbers. Okay. So all that I have left to do now to find the area between is subtract the smaller area from the larger area. Okay, so you can see below, I'm carrying out this particular calculation. So I have 0.9750 minus 0.0250, which is 0.9500. Okay. So the area between the positive and the negative in this, well, the area between positive 1.96 and negative 1.96 is a size of 0.950. Any questions? It's okay. That's good. Simple is better. Any other questions or comments? Good, 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 good. Okay, so, oh, yeah, all right. Okay, so we looked at 3 different illustrations. Area, do I not do a, oh, I save it as an exercise because I guess I'm a dick. All right, so we've looked at 3 different illustrations. There's one case that we haven't talked about yet that we will see in the exercises that are gonna follow this slide. We learned how to find area to the left of a value. We learned how to find area to the right of a value. We learned how to find area between 2 values. The only thing we haven't done is finding area to the outside of 2 values. So something below a negative and something above a positive. But that would just be a combination of rule 1 and rule 2. In all situations, I strongly suggest that you sketch out what you're looking for before turning to the normal table. But if you really don't want to, you don't have to, but it's only going to make your life easier, and the sketches don't need to be super precise. Like this isn't I'll show you how I'm going to sketch it. It's a very quick, like here's my curve and this is what I need. Okay, so we're going to do 4 different exercises. The first 2 exercises we have already seen examples of. The last 2 exercises we haven't actually seen examples of yet, but they're combinations of below and to the left and to the right of 2 z-scores. All right, so example 1, find the area to the right. No, I think that, is it still lagging? The internet is not very good on campus, so. Okay, yeah, sorry, Alice, it might be yours. Is it? Oh, she's gone. Yeah, definitely. It's unfortunate. Okay, so we're gonna work through these 4 exercises. Hopefully I can finish them today. So exercise 1, we want area to the right of 2.09. Okay, so step 1, sketch. So this is gonna be my sketch. You can see it's a very quick sketch. I just marked down where 0 is at the center of the curve. Now I'm just gonna roughly place where 2.09 should be located. Again, this doesn't need to be precise, right? Like you just have to have, the beauty of a normal curve is that you always have reference to the mean because the mean is always at the center. We're working with standard normal curves, so our center is always 0. Okay, now I'm gonna shade what I want. So I'm looking for area to the right of 2.09. Okay, so this problem is basically just what is the probability that Z is greater than 2.09? Okay, this is going to be 1 minus the probability that Z is less than 2.09. Okay, now what I need to do is get my normal table. So I need to, here are my tables. Here's my negative, and here's my positive. Okay, so I have a z-score positive 2.09. Okay, so here's page 1 of my normal table. Page 1 are all the negative values. That's not useful to me right now because I want the positive values. So I go to page 2. Okay. Now what I'm going to do is look up 2.09. So here's 2.009. And here's 0.9817. Okay, so what I have found here is the area to the left of 2.09. So this is the probability that Z is less than 2.09. Yeah, because it's closer. Yeah. Yeah, so the question is, I guess you must be working ahead, right? So say you're looking for a number inside of the table that's 0.89. There's a value in the table that's 0.888, and 0.8907, you would choose 0.888, right? Yes, because it's closer to the value that you are looking for. Okay, so I looked up the probability that Z is less than 2.09, which is 0.9817. So this area is 0.9817, and that gives me 0.0183. All right. Okay, any questions? All right. Numero 2. We want the area between negative 1.645 and 2. All right. So, no. Okay. So I start by sketching my curve. All right. Here's 0. I want to be between negative 1.645 and 2. So I need to mark down my values. Okay, so Z equals negative 1.645 is here, and Z equals 2.00 is here. Okay, I want to be between these two values. Right. So I have probability negative 1.645 is less than Z is less than 2.00. This is equal to the probability that Z is less than 2.00 minus the probability that Z is less than negative 1.645. All right. Okay, so now all I need to do is look up positive 2 and negative 1.645 in the normal tables, because these are both areas to the left. Okay, so we'll start with positive 2. So I have 2.00. Here's 2.00. That gives me 0.9772. Okay. Okay, now I need to look up negative 1.645. So here's negative 1.6. Now this is a special case. So I have negative 1.645. So in the third spot, I have a 5. In that situation, you have to take the average of the two values. In any other case, you would round. So if it was negative 1.646, you would just round up to negative 1.65. If it was negative 1.644, you would round down to negative 1.64. We have negative 1.645. So because we have a 5 in the third spot, we're going to take the average of negative 1.64 and negative 1.65. Okay, so we're going to take the average of 0.0495 and 0.0505. Okay, so we can write this as 0.0495 plus 0.0495 plus 0.0505 divided by 2. Okay, so that's going to be 0.9772 minus 0.05, which is 0.9272. Okay, any questions? You know, when you're on the phone with someone and you don't want to continue the conversation, so you do like the fake signal thing isn't working, like, oh, it's breaking up, I can't hear you. I feel like that's what happened with that student. She's like, oh, is it lagging for anyone else? That's weird. And then she just left. Anyways. All right. Number 3. Oh, well, that's embarrassing for me. Welcome back. And I guess technically it wouldn't be necessary because you could just leave, right? Like, why make a scene about it? All right. Jessica, negative 1.644. No, so negative 1.644, you just round down to the 2 decimal place. So you would take negative 1.64. It's only in the case where the 3rd decimal spot is a 5 that you average. In any other case, you round to the closest 2 decimal place number. Does that make sense? Okay. All right, we should have time to do one more. So find the area below negative 1.645 and the area above positive 1.645. All right, so that's 0. I have positive 1.645. I have negative 1.645. Okay, so I want the area above the positive and below the negative. Okay, so this is the probability that Z is less than negative 1.645 plus the probability that Z is greater than positive 1.645. Okay, so this is the probability Z is less than negative 1.645 plus 1 minus the probability that Z is less than 1.645. Okay, so we actually already found the probability of being less than negative 1.645 in the previous illustration. So this, again, for the exact same reason discussed above, will be that. Okay, now what we need to do is find the area above positive 1.645. Okay, now we actually should already have a very good idea of what this is going to be because of the symmetry of the curve. So since the area to the left of negative 1.645 is 0.05, the area to the right of positive 1.645 is going to be the same thing. But we can show that that is true by looking up the area to the left of positive 1.645. So we go to our normal table. Here's 1.60405. We're going to average again because the 3rd decimal spot is a 5. So we're going to take the average of 0.9495 and 0.9505. Okay, so this is going to give us 0.05 plus 1 minus 0.95, which is equal to 0.1. All right. Okay, any questions? I have a question. Why did I write so big? Yeah, it's totally fine to do that. I just don't want to get carried away with abusing symmetry. I just want to show you how you would do it step by step by step. But if you're okay with it, then it's fine to do it the other way as well. Okay. So I am going to stop here for today. On Tuesday next week, I'm going to do the last example as a refresher, and then we're going to talk about all like 3 different things that you can do with normal tables. Those 3 things are effectively going in the opposite direction. So we have started with the Z-score and found area. We're going to talk about how you start with area to find a Z-score. And then we're going to generalize those 2 situations to any normal curve. So far, we have only seen how to find area under the curve using Z-scores. But you can do this with any parameter set for any normal curve. We just have one more additional step. And then we can also go in the opposite direction to find a Z-score given area. And the reason we would want to do this is so that we can define percentiles of the normal distribution, which is going to be probably going to occur in a couple of spots on assignment 3, and it'll also show up on the midterm. Okay, so have a good weekend. Assignment 3 has been posted. You can certainly get it started at this point. There's lots of Z-score problems on there. And I will talk to you guys on Tuesday. Lab quiz. Is it not? Wouldn't it have opened? Yeah, okay, tonight at 8. Okay, yeah, thanks guys. Sorry. Yeah, so have a good weekend, and I'll talk to you guys on Tuesday morning. Okay. Does anyone have any other questions about the material? Oh, I guess there's no one. Yeah, Ram. Oh,